Now let's consider this a two-mass spring damper system with base excitation. We have a wheel running over a road profile as shown, and base excitation is a form of forcing on the system. So we will move on with the analysis that we discussed for forced multi-degree freedom system. Now we have two masses connected by springs and dampers, and the values for the masses are given 0.5 and 2 kilograms. The damping is 30 and 40 newtons second per meter, and the stiffness of the springs is 150 for the first and 200 newton per meter for the second spring. Now these values are selected carefully so that we will have proportional damping in the system, so we can proceed with the decoupling procedure that we discussed in the previous video. Now, so we have these two masses running with a speed of 10 meters per second over this road profile. Now this road profile is the height of the road as a function of the distance along the road, but our force should be function of time. So I have to convert these distances, the 5 meters, the 60, the 5, into time. And how we do that? We know that the speed is distance divided by time, which means that time is distance divided by speed or velocity. So our velocity here is 10 meters per second. The distance, the first distance is 5 meters. So the time to cross the 5 meters is 5 divided by the velocity, which is 0.5. So the first time is 0.5 seconds. The wheel runs starting from 0 in 0.5 seconds. It will rise to 20 centimeters, that is 0.2 meters. So this is 0.2. Then this is y of t. And then 60 meters with a velocity of 10 meters per second, 60 by 10, that's 6 seconds. We need 6 seconds to cross this section, so that this point is actually 6.5. 6 seconds and the 0.5 second. So here, crossing at a height of 0.2 meters, and then another 0.5 seconds to drop back to 0. So this is at 7 seconds. 7.0. We go down to 0 and then continue. So this is the time axis, and this is y of t, assuming that this is y of t. The wheel will follow the profile of the road, and let the motion of m1 be x1, and the motion of m2 be x2. So now we need to go ahead and derive the equations of motion. Again, here it's a one-directional motion, so you can use either the energy method or the Newtonian approach. Newtonian approach is straightforward because it's a one-directional motion. So you can just draw two free body diagrams for M1 and M2 and use the sum of forces equals M times the acceleration to derive the two equations of motion. So here I can now extract the inertia, damping, and stiffness matrices. The inertia matrix M is going to be M1 times x1 double dot, nothing times x2 double dot, nothing times x1 double dot, M2 times x2 double dot, and this is the inertia matrix. The damping matrix multiplying x1 dot is C1 plus C2, multiplying x2 dot is negative C2, and to the second equation, negative C2 multiplies x1 dot, and C2 is the coefficient of x2 dot. Finally, the stiffness matrix is x1, k1 plus k2, x2 is negative k2, and on the other equation, negative k2 x1 and k2 x2. The force vector now, F vector, is force in the first equation is C1 y dot plus k1 y, and in the second equation we have a 0. So now here's the system matrices and forcing vector. Now if you plug in those numbers here, the inertia matrix will become 0.5, a 0, a 0, and a 2. The damping matrix is going to be 70, negative 40, and negative 40, and 4, 0. The stiffness matrix, 350, negative 200, negative 200, and a 200. As for the force vector, C1 is 30, so this is 30 y dot plus 150 y and a 0. Now, first I need to solve the eigenvalue problem for the eigenvalues and the eigenvectors. I have the inertia matrix and I need the stiffness matrix only, because my eigenvalue problem is k minus lambda m times x equals 0. So only the stiffness and the inertia matrix. So now if you plug in these two matrices either into MATLAB or just find the determinant of k minus lambda m and solve for the eigenvalues of eigenvectors, we will get the lambda 1 equals and p1 equals and lambda 2 and p2, two eigenvectors and two eigenvalues. Using manual calculations, here are my two eigenvalues, which are the squares of the frequencies, and the two eigenvectors, which makes the matrix of eigenvectors 1, 1.651, and 1 and negative 0.1514. Now my next step would be decoupling the system. The system is M Q double dot plus C Q dot plus K. Q is F. So I need to decouple the system. I need to find P transpose M P, and that would be M tilde, and I need also P transpose C P, that would be C tilde, and P transpose K, P for K tilde, and finally I need to multiply transpose P times the force vector for F tilde. Okay. So now here are the decoupled matrices. As we see, all matrices are now diagonal, even the damping matrix, because of the values that were selected carefully so that we have proportional damping. Now, this means my equations of motion are now in terms of the modal coordinates eta m eta double dot plus c tilde eta dot plus k tilde eta equals f tilde. So my equations of motion are going to be 5.954 eta 1 double dot plus 6.97 eta 1 dot plus 234.9 eta 1 equals 30 y dot plus 150 y, and for the second equation I'll have 0.5458 eta 2 double dot plus 83.03 eta 2 dot plus 415.1 eta 2 equals 30 y dot plus 150 y. So now we have two single degree freedom problems. Basic citation. Basic citation is basically some type of forcing. This right hand side is just the force, f of t, except that the force now is a result of the profile of the road, y of t. Now I can also determine the frequency and damping ratio of each mode. For example, here we can divide k by m to get omega squared, and then divide c by m to get 2 zeta omega n, and I can determine zeta 1 and zeta 2. Omega 1 is, omega 1 squared is 234.9 divided by 5.954, and that's going to be actually the first eigenvalue, which was 39 something. And I know that 2 zeta omega 1 is c over m, which is 46 divided by 5.9, and then I can determine zeta 1. So I can determine the amount of damping in the first mode, eta 1, and I can determine zeta 2, the damping in the second mode. Now, to proceed further, now to determine the forced response, I will write down the transfer functions. G1 and G2, G1 of S for the output eta 1 of S and the input Y of S. My input is the road profile. So you take the Laplace of this equation. The transfer function is going to be 30S plus 150 divided by 5.954 S squared plus 46.97 S plus 234.9. That's the first transfer function. And the second transfer function, G2 of S, which relates eta 2 to Y of S, is going to be 30S plus 150 divided by 0.5458 S squared plus 83.03 S plus 415.1. So these are my two transfer functions. Plugging these transfer functions into MATLAB, my output would be, my input is Y of S or Y of T into G1 and G2. The output is going to be eta 1 and eta 2. But now I'm looking for x1 and x2. My original transformation was Q equals P times eta. So Q is actually the generalized coordinates x1 and x2. Equals P is right here, the I matrix of eigen vectors 1.1651 and 1 and negative 0.1514 times eta 1 and eta 2. So that means after determining eta 1 and eta 2, I know that x1 is eta 1 plus eta 2. So x1 of t equals eta 1 plus eta 2, and x2 of t is going to be 1.651 eta 1 minus 0.1514 eta 2. 651 eta 1 minus 0.1514 eta 2. So I have these two equations. I can use a multiplexer here and put the two signals, eta 1 and eta 2. I get u, which is basically the vector eta, which includes u1 is eta 1 and u2 is eta 2, and use this on two user-defined functions, f of u, f of u, and the output here is going to be x1 and x2. Inside this block, I will have this equation, which is basically eta 1 is going to be u1 plus eta 2 is u2. That's inside this block. And inside the second block, it's going to be 1.651 times U1 minus 0.1514 times U2, which is eta 2. Insert these equations into these two blocks and you will get eta 1 and eta 2. You can either store the values or stick a scope at the end of each line and observe the motion of the masses, x1 and x2. So this is how we deal with forced damped multi-degree freedom systems, but this is, as I said, it's a special case where we have proportional damping.